Okay, let's move on to a new chapter. This is chapter 3, Discrete-Time Systems. Discrete time, which I'll often abbreviate DT. A lot of the material in this chapter will seem very familiar. It's quite similar to material that we covered with regard to analog systems. So first, just a brief introduction to discrete time signals. So a discrete time signal is actually a sequence of numbers which will denote x of n. Traditionally, square brackets are used to surround the argument here so that you can easily distinguish a discrete time signal from a continuous time signal. We can plot a discrete time sequence. Consist of a series of just values at particular integer values of the argument n. Might be positive or negative values, but this would be a discrete time signal. Again, it can go, it could be infinite in duration, starting either at minus infinity and then perhaps going to positive infinity. Just a note on Octave Matlab, typically you would, in Octave or Matlab, a sequence is represented by an array, and you'd graph a sequence using stem, not plot. So, for example, if I define an n vector as going from minus 10 to n, minus 10 to 10, and then I can define a discrete time signal, I can still use my delta functions that I've used in the past. A delta 2 would be a ramp. And then I can plot this sequence like this. Here's the argument, and then here's the corresponding array. The plot Octave would then produce, in this case, since it is a ramp, it's 0 at 0. It would have the value 1 at 1 and 2 at 2, going up to, in this case, we have the value 10 at n equal to 10. So this is my discrete time axis. And then for all negative values of n, it would be 0. Of course, I can create a shifted ramp. Just substitute n minus 2 would shift this function 2 units to the right. So we can define a discrete time signal directly. An example of a discrete time signal in practice in the real world might be the closing stock index at the end of the day every day, or temperature taken at a particular time every day. So these aren't continuous in nature. We could also obtain a discrete time sequence by sampling a continuous time signal. So as an example, if we sample the continuous time signal x of t is equal to e to the minus t, every capital T equal 0.1 seconds, that would generate the following sequence, x of n, and I substitute n times capital T. So I would, with n equal to 0, I would sample at t equal to 0. With n equal to 1, I would sample at little t equal to capital T, or 0.1 seconds. With n equal to 2, that would be a sample of x of t at little t equal to 0.2 seconds. So plugging in little nt for little t, I get e to the minus nt, or e to the minus 0.1 n. And then so I can sketch this sequence as a function of n. So starting at 0, at n equal to 0, e to the 0 is 1. And then at n equal to 1, I'd have e to the minus 0.1. Evaluate that, and I get a decreasing exponential sequence exists that will continue on forever. Of course, for negative values of n, it would continue to increase back in this direction. Similar to what we did for continuous time signals, we can characterize the discrete time signals by what we'll call their size. And this is not typically their amplitude, but rather we'll have commonly encounter two types of signals. Energy signals, for which we can compute the energy. It's the sum over all n from minus infinity to infinity of the squared sample values. Okay. Now, this is typically finite, a finite sum for most pulse type signals. We also have power signals. A classic example of a power signal are the periodic signals. We can calculate the power of a discrete time signal. Is defined in a limiting operation as n goes to infinity, capital N goes to infinity, of 1 over 2n plus 1, the sum from n equal minus capital N to plus capital N, again of the sequence squared values. So the definitions here are similar to the definitions that we use for continuous time signals, except instead of integrating, we're actually summing. For a periodic signal, we can do this averaging operation over only a single period to obtain the power. In that case, we divide by the period, and then sum over, we can sum actually over any period, so any n0 adjacent samples. So this is usually the formula we use anytime we encounter a periodic signal, again, where n0 is the period. And we'll see some examples of discrete time periodic sequences or signals in subsequent lectures.